I'm Julien Serres from Aix-Marseille University, and my talk is entitled MiMiC-ANT Project, Study of Locomotion During Load Transport in Hands, Application to Hexapod Robotics. It presents research carried out in both Marseille, France, at the Institute of Movement Sciences, ISM, and in Toulouse, France, at the Animal Cognition Research Center, CRCA. My coworkers are Vincent Fourcassié, Ilya Brodoline, Pierre Moretto, and Stéphane Viollet. Now, I'm going to talk how the ISM and CRCA work together on the MiMiC-ANT project. You can see on this slide a desert ant, Cataglyphis nodus. It weighs from 10 to 20 milligrams and can walk as far as 150 meters with a capability of load transportation up to 15 times its weight. Ants are the best biological model to study the load transportation because they can transport the heaviest load with respect to their weight of the animal kingdom. Trying to mimic and to rebuild ant from a biomechanical point of view could be helpful in the hexapod robot design. For instance, the handbot robot weighs 2.3 kilograms and can travel 10 times a journey of 15 meters without breaking down. Servomotors are particularly sensitive to temperature, and plastic gears are extremely fragile. The handbot load transportation ability is only 0.3 times its weight. The MiMiC-ANT project was helpful to better understand the gap between ants and hexapod robots, to bridge the knowledge between ants and robots. The CRCA has expertise in both ants morphology and locomotion, and the ISM has expertise in both artificial sensing and robot design. So, our research question is here: how can we take inspiration from ants to improve the load transport in hexapod robotics? Let's start with why are ants a good model for the development of innovative locomotor pattern strategies in hexapod robots. First of all, because of their great biological diversity, there are currently more than 13,000 species of ants in the world. These ants live in very diverse environments from the canopy to the ground. They move on very varied substrates, which can sometimes present a strong roughness and constitute very uneven substrates. Because of the diversity of the populated environments, ants also often present specific morphological and behavioral adaptations, which are often remarkable. You are two examples here. The first pictures show a worker, the genus Cephalotholes, also called turtle ant. These ants occupy galleries drilled by wood-eating insects in the tree trunks. Some individuals in the colony have a deformed and flattened head, which allow them to block the entrance of the galleries. The second example shows a worker of genus Melissotarsus, which also lives in galleries inside the wood and whose second pair of legs is turned upwards, which allow the ants to lean on the ceiling of the galleries and to crawl better in them. Finally, ants have the particularity, quite unique in the animal world, to carry loads either individually or collectively. In some species, the loads carried can weigh up to 15 times the weight of the individual. We can therefore draw interesting lessons for the development of load-carrying hexapod robots from the way these insects adapt their locomotion pattern according to the weight of the load they carry. Now let's move on to a small recall on the locomotor system of insects, and ants in particular. Like all insects, ants have 3 pairs of legs. Each leg has a different length and is formed of 5 segments: the coxa, the trochanter, the femur, the tibia, and the tarsus. At the end of each tarsus are usually claws that allow the hand to cling the substrate. The joints between the different segments are of different types, as can be seen on this illustration. The sensory feedback on the position of the legs during locomotion is based on the stimuli provided by mechanoreceptors that are distributed at different locations on the legs. The campaniform sensia are, for example, a type of mechanoreceptor that are located at the coxa and trochanter and are sensitive to the stress on the cuticle. The legs are actuated by muscles that are anchored on apodems of the exoskeleton and that can sometimes cross several segments, as here in red, the muscles of the trochanter that cross the coxa and that are anchored on the upper part of the thorax. To study locomotion in ants, we used the following device. Ants move on a horizontal platform. They are filmed by 5 high-resolution cameras at 250 frames per second. The platform is illuminated by 4 infrared spots which are synchronized with the cameras, which allow to have a better contrast between the ants and the background on which they move. The videos are then analyzed by a Kinovea software which allows to follow in semi-automatic several points of interest on the body of the ant, in particular the ends of the legs. The results show that ants are able to adapt their locomotor behavior to the load they carry in order to increase their stability. This stability is indeed put at risk by the load they carry, which shifts their center of mass towards the front. The 2 graphs you have here are podograms. They show the sequence of support and lifting of the ant's legs as the function of time for an unloaded ant on the top graph and for the same loaded ant on the bottom graph. The color coding on the bottom of each podogram indicates the number of legs simultaneously in support. The top graph shows that the locomotor pattern observed for an unloaded ant is fairly consistent with the locomotor pattern encountered in all insects. The locomotion is said to be in alternate tripod. The 2 tripods are formed respectively for the first one by the right front to back leg and the middle left leg, and for the second one by the left front and back leg and the middle right leg. We can see on the podogram of the unloaded ant that the gait of the ant is more or less in accordance with this diagram. For the hind legs, we notice that they are often dragged on the ground rather than lifted. For the loaded ants, on the other hand, the locomotor pattern is alternate tripod is largely disturbed. We notice that the number of legs simultaneously in support is more important than in the unloaded ants. The analysis of the videos also showed that the middle legs are further away from the axis of the ant's body in loaded ants. Both of these changes increase the area of the support polygon and thus the static stability of the ant. In relation to the above, we also observed that kinematically the load transport does not affect the length of the strides, but on the other hand, it decreases their frequency, which leads to a decrease in speed. Finally, we observed that the hind legs are dragged less on the substrate in hands carrying a load on this, and this is probably related to the fact that hands cling to the substrate with their claws during the support phases to avoid tipping forward. Together, these results show that the typical alternating triple locomotor pattern of insects is largely altered in load-bearing hands. The alternating tripod gait is therefore not a rigid locomotor pattern, and ants are able to adjust their locomotor patterns in order to increase their stability when carrying a load. In this short video, you can see the handbot robot working from its starting point. The handbot robot is fitted with a battery and can work for about 15 minutes. That's why you can see a power supply with a cable to work all day. The handbot is motorized with servo motors, consuming a large amount of energy and highly sensitive to outdoor temperatures, with maximal working temperatures up to 70 degrees Celsius. It is quite difficult to make the handbot generate more than 10 trajectories of 15 meters without having to change one servomotor, because the plastic gears were particularly fragile, mostly during summertime experimentation. Currently, two categories of robots are used to study insect locomotion and navigation behaviors. The first category, like Drosophilbot and handbot, are robots specially constructed in laboratories for a particular task. The second one corresponds to the hexapod robots available on the market, developed for a general use and education. For both categories, the mass, autonomy, performance, and price range are the same. Some differences correspond to the structural accuracy and the embedded sensors. All the previously presented robots are actuated by servomotors, a classical motorization choice for hexapod robots. Servomotors are simple to implement, easy to control, compact with a large choice of models on the market. Such characteristics explain their wide use in hexapod robotics. However, important drawbacks are also present. Servomotors have a weak gear system, which is generally partially composed of plastic gears, and overheating, which makes it difficult to work in outdoor environments, mostly in summertime. One of the main drawbacks is also the continuous power consumption, as shown by the figure. A 18 degrees of freedom servo-based hexapod robot in a static position has a continuous power consumption equals to one or two servomotors in movement, which of course limit the autonomy and range of the robot. To overcome these drawbacks, a new actuator structure was chosen, which is based on a classical worm gear mechanism. This new actuation structure keeps the same torque-speed ratio as a servomotor, but reduces the cost and improves the durability of the actuator. The key idea of this new mechanical design is to work with a non-reversible joint in order to block the mechanical structure when the motor is not actuated, then setting to zero the power consumption. Based on the irreversible worm gear structure, we constructed a novel hexapod robot's leg. This leg is composed of 3 degrees of freedom as often encountered in insect-inspired legs model. The dimensions and the angles of the leg segments fit suitably with a Cataglyphis fortis ant leg, with a scaling factor of 30. The leg is fully printed in 3D, which reduces considerably the manufacturing price and potentially reparation costs. To add some compliancy in the leg structure, 4 sensors were implemented at strategic locations in joints. The force sensors are composed of a slider and a spring in each joint. Consequently, the force measurement is done at the level of the joints and not at the tip of the legs, as often encountered in hexapod robotics. Such a force sensing mimics the campaniform sensilla organs in insects, which are mechanoreceptors taking part in locomotion control. 2 new legs have been designed in the framework of MiMiC-ANT project. On the left hand, we can see the presented leg structure working on the test bench, also called MiMiC-ANT. On the right, a reduced version of this same leg, but fully 3D printed. The main difference apart the scale is the presence of compliant joints composed of soft segments like insect tendons, which both simplify the leg structure and reduce the weight. A test bench was developed to analyze the performances of our new robot's leg and evaluate the advantages compared to a classical version servomotor-based leg. This test bench is composed of a treadmill, ground force sensors, motion capture cameras, thermal imaging module, and current measurements. This test bench reflects the experiments typically carried out on insects to study their locomotion. The resulting data of the test bench, grouped in a characteristic table, detail the tested leg performances. What are the expected level of performance of the 2 new hexapod robots, Pohod15 and Pohod15 Junior? This table presents the expected level of performance of the new developed robots compared to the Antbot robot and the 3GOF Phoenix hexapod robots, both based on servomotors actuators. Keeping the performances in terms of mass, payload, and speed, 2 main features have been usually improved: the autonomy in range, potentially twice better, and the cost, potentially half cheaper and easy to fix, which reflects what we can expect with these 2 new hexapod robots. To conclude and to give some future works, the MiMiC-ANT project has allowed us to better understand the gap between hexapod robots and hands, leg morphology, force sensing, legs coordination, and cost of transport. An experimental setup has been developed to understand the load transport in hands. Hands adjust their locomotion pattern while transporting a load. A setup to measure ground reaction force in ants is in development in 2021-2022. 2 kinds of legs comprising non-reversible joints and force sensing have been built. The expected level of performance should be at least twice better with respect to conventional leg. A MiMiC-ANT test bench have been built to evaluate the benefits of the new bio-inspired legs with respect to a conventional leg design in 2021. Building the 2 hexapod robots Pohod15 and Pohod15 Junior will be the next step in 2022 to mimic locomotion pattern adjustments observed in hands while transporting a load. The MiMiC-ANT project was granted by the CNRS the University of Toulouse 3, the University of Aix-Marseille and DGA, Direction Générale de l'Armement, the French Defense and Security Agency. Thank you for your attention.